like, how much, like, do we need to memorize the urea cycle like we did glycolysis, sorry, or like, what do we really need to take out of the last 30 slides for that?
Okay, so not having reviewed all the data in those last 30 slides, I can tell you that the actual pathway, she'll test it similar to other pathways, where it's knowing where the molecules are placed one after the other and memorizing that is useful so that you know where you are in the body. But she's not going to say, what's the step after blah, blah, blah. Yeah. She's going to ask you about the diseases, and those are at the beginning of it. And then she might ask you about the enzymes that might be broken or not, or maybe the enzyme that gives you the final product.
Yeah,
arginase in that case.
Okay.
So,
okay.
Hey guys. So today we're going to be going over nitrogen metabolism and about urea cycle and kind of just QA style. Maybe we'll go through the whole thing. It's what we did last week, but we did that preview, and now that's where we still are. So, glad you're here. Okay, so yeah, that's how I would do the urea cycle pathway is learn it, but focus on the diseases. In the last 30 slides, did she talk about anything else? Like 30 slides for the urea cycle that's a lot of slides for people. Oh, I bet he has a single slide for like every molecule or something.
Mm-hmm.
Okay.
Every step.
And then thankfully she has that one slide where it's all together. And that slide is the one that you want to look at. That's the one that's helpful, and I really like that.
I can't decode that though. That's too much on there.
Okay, well then we will work on decoding. I wish I could remember what the German decoder thing was in World War II, because that would be a great joke.
And aphids when I look at it.
Okay, the erasers are fired, and we will begin. So, let's go ahead and start just with the urea cycle itself, since that sounds like, is that good with everyone? The actual, like, deciphering that?
We're starting with urea, we're not going to do nitrogen?
We will do that too. It's like whatever you guys want.
Nitrogen, please.
Nitrogen, urea, we want the whole thing. Okay, so I'm going to do a sketch of the urea, then we'll do nitrogen, then we'll do urea in detail at the end. So here's the sketch of the urea that'll help make sense of what the freak is going on, and then hopefully that will turn it into a beautiful slide. So they show 2 shades of background. One shade represents inside the mitochondria. The other shade represents just in the cytosol, so inside the cell, but not in the mitochondria. In the mitochondria, we'll discuss where this comes from, but magically, we have some ammonia or nitrogen in some form floating around. And because it's everywhere, we have some CO2. We also have water. H2O. If you put these guys together, there are 2 enzymes. The first one, I'm not even sure if I think it's the first
enzyme. Phosphate synthase 1.
That's the one that's on this particular, so let me go ahead and circle in red right here, the one bit that is not on that. This first enzyme is not on that slide. Everything else is. So these are all put together into a precursor molecule. And then that precursor molecule is acted on by carbamoyl phosphate synthetase 1. Carbamoyl phosphate synthetase 1. It's a synthetase, so it takes ATP. Synthase means it's free, synthetase means it takes ATP. And this one takes 2 ATP, if I recall correctly. This will make it into carbamoyl phosphate as your molecule. So, pieces put together into a thing that is a precursor to urea. This is going to be what is going to become urea. The next molecule I'm going to say is actually just a carrier molecule. And that carrier molecule is ornithine. And ornithine is going to go ahead and pick up carbamoyl phosphate using ornithine trans carbamylase. So it's just this name, transfer this name. And then it gets its whole other name, citrulline. But citrulline is just a way of saying ornithine holding carbamoyl phosphate. And I'm not going to write out all the rest of the steps, but I wanted to write these ones because the concept is ornithine carrying carbamoyl phosphate is called citrulline, but it's still just carrying it. And then it will move out of the mitochondria. And then there's a bunch of other steps, and all those steps is flicking the carbamoyl phosphate into different shapes while the ornithine holds it. And then eventually, it looks like urea, and it lets it go. And then what do you have left after it lets it go? The carrier. And the carrier, after it's gone through its whole cycle, will come back inside the mitochondria, ready to do it again.
Ornithine is the carrier.
Right. And so that's the concept of what's going on here. The things that she might want you to know, there's a disease here, even though she won't, I don't think she'll ask you this enzyme, but see if you can find it in the slides. Maybe I went and looked it up myself because I heard about it and I was really anal, and that's why I can't find it again. But there's a disease here, and then there's a disease here. It's really dangerous to have free ammonia, free nitrogen. And so if you can't make it into something safer, then you're going to have problems. We'll talk about it more, but basically it will go and cause your brain to not brain anymore, and then you die. It's bad. So if this first guy is broken, you have no buffer. So the ammonia has nowhere to go. It'll build up inside the liver where this is happening.
Liver.
And go to the blood, go to the brain, bad. So this one is really like triple, double, extra bad. If you have this first enzyme though, but you don't have the second one, then you can turn a whole bunch of nitrogen into this semi-safe intermediate molecule. And that's okay until you can't keep moving it. So then this builds up a whole bunch, and then you stop being able to move the reaction forward because you have a whole bunch of this specific product. And so if you have a lot of product, it's going to move back towards reactants, and then eventually you have the same problem again, where you have a bunch of free nitrogen because you can't keep making more of this little intermediate molecule because there's too much of it already. What's the point? This one gets bad fast. This one gets bad a little bit slower. You have more wiggle room with the second one. And these two diseases have the same name. And if anyone has the slides and can look at what that name is, that'd be great. We'll come back and hit all of this in more detail. But did that help for the urea cycles concept? Kind of, sort of, maybe. Is there any other specific question about it?
So are you talking about hyperammonemia?
Yes. Hyperammonemia type 1, type 2. Thank you. When it's in the name, I find it the hardest to remember it because I'm always like, it's like the name. So
you gave me that you forget it.
Hyperammonemia. Type 1, the bad one. Type 2, the one that you have a little bit more time. So, hyper means too much. Ammon meaning ammonia, meaning nitrogen. Emia means in the blood. So, too much nitrogen in the blood, type 1, type 2.
This slide is saying that hyperammonemia is due to a defect in the carbamyl phosphate synthetase.
And that's type 2. And if it's broken,
well, this slide says type 1.
Type 1, does type 2 have it on the same one?
Type 2 is due to deficiency of ornithine transaminase.
Okay, sweet. Then that makes a lot of things make sense. Everything is still true about the two of them and about the buffer situation. It's just that carbamoyl phosphate is the buffer, and then citrulline, so you have carbamoyl phosphate synthetase 1 is your first enzyme, and then ornithine transcarbamylase is your second enzyme. And so it's still type 1 and type 2. Type 1 is the triple, type 2 is you have a little bit of buffer time, and the buffer molecule is carbamoyl phosphate. So, excuse me for shifting the molecules up one. Still the same story though. Any clarification on that since we had to switch it up? Yes, good. Yes, clarification. Okay. So all these three ingredients, carbamoyl phosphate synthetase 1 grabs them and turns them into carbamoyl phosphate. If you can't do that, then you're going to build up ammonia really fast. If you can do that, then you'll build up a whole bunch of carbamoyl phosphate, but if the next enzyme is broken, then that can build up, and then that spills back because you have a bunch of product, therefore you're going to end up getting reactants again, and so then you'll eventually have a lot of ammonia that way too. So this guy broken, fast, bad. This guy broken, eventually bad. Better? Apologize for saying it the wrong way the first time. All right, any other questions on this? All right, in that case, let's go through nitrogen metabolism.
I do have one question.
Okay, what's the question?
It says that enzyme carbonyl phosphate synthetase 1 is positively regulated by the allosteric effector in acetylglutamate.
Okay.
Do you know what N-acetylglutamate is other than being a regulator?
And acetylglutamate, I'm not recalling that she wanted you to know more about that, but she does want you to know regulators in general. And so
It's in red.
this one costs energy, right? And so we know that it's going to be very likely a regulated step. That's why I make a big deal about energy, one of the reasons. And so you would want to know that it's regulated, and since N-acyl glutamine, glutamate, and that makes sense because glutamate has nitrogen in it, and so if you've got a whole bunch of this around, then it'll be saying, hey, we need to make urea out of some of this. So this turns on make urea. So that's the answer to that. And there are a couple other enzymes and stuff we can throw in here, but I want to make sure we have time for the nitrogen metabolism. So, all right. Good question, though. I'm glad you brought up the regulation.
So just to clarify, sorry, it's fine, keep going. The hyperammonemia type 1 would be a defect in the CPS1 enzyme.
Right.
And hypoammonemia type 2 is in a problem with the ornithine transaminase.
Exactly. Yes. Okay. Now, nitrogen metabolism. There are a couple times when we would need to deal with nitrogen in the body. That can be either when we're in starvation and we're like, we've got to break something down for energy. Let's start breaking down our muscle. That's what we've got. So that's one reason that we'd be breaking down amino acids. And amino acids, let's go ahead and draw what they look like. So an amino acid has a carboxylic acid, or carboxyl. It has a nitrogen group, has a hydrogen, and then it has an R group. The R group stands for any kind of shape that you want, specific to each amino acid. That's what makes the amino acids different, is that they have different R groups. The rest of this is the same. So the ammonia, the nitrogen group, is actually toxic. And so rather than just breaking this down for energy and then letting it go free, that would cause problems. So we have to break these guys down specially. One time during starvation. Other time, if you eat a lot of amino acids, you will use them for protein and for building muscle and for making all the machines inside your cells as much as you need to, but then you're probably going to have extra, especially if you have a typical diet in America. And so you're going to break them down then too. starvation for desperation energy, overeating protein. Both of them lead to needing to break down these guys. So when we're breaking them down, they get some special names. We're going to go ahead and take off the nitrogen, and that nitrogen can, and that way he's not free, because free is toxic. We'll talk about why. But what do we call the rest of this? Because now it's got a hydrogen up here, and there's nothing left, and this is going to be called either a carbon skeleton or an alpha keto acid. So these two terms are not quite synonymous. We'll go over the difference, but both are true. This is both a carbon skeleton and an alpha keto acid. Carbon skeleton means carbon structure left over after you take off the nitrogen. So like all the nitrogens are gone, it's a carbon skeleton, no nitrogen. Alpha keto acid means structure after you remove one nitrogen, structure minus one nitrogen. Usually that means no nitrogens are left, but sometimes something might have two nitrogens. Then you could have an alpha keto acid that still has a nitrogen. And so is it a carbon skeleton? It's still got one nitrogen left? No. That's why these aren't quite the same. Usually they are. All right, so let's bring in glutamine. Glutamine, two nitrogens. Take off one. Glutamate, one nitrogen. Take off another one. Alpha keto glutarate, which is a molecule. This isn't the same thing. Where have we seen alpha keto glutarate? TCA cycle. So this is directly inside the TCA cycle. And that's great because what we want to do with all of our carbon skeletons, this is one example of a pathway to get to a carbon skeleton. And this is a pathway that she will want you to know. Those carbon skeletons are going to be burned for energy. And so it's already in the TCA cycle, which is where we burn things for energy. So this guy is going to give us close to 10-ish. You don't need to know the number, but it's going to be burned for a good amount of energy. And he has 0 nitrogens. All right, pop quiz. If our original molecule was glutamine, first answer in your head, then we'll check out loud. If your original molecule is glutamine, which of these, and there might be more than one right answer, which of these would be the carbon skeleton? In your head first. Question 2. Which of these, if not both, would be glutamine's alpha keto acid? Okay, answer to question 1. Carbon skeleton, this guy. No nitrogens. Answer to question 2. Glutamine's alpha keto acid would just be glutamate, not alpha keto glutarate, because it's minus 1 nitrogen. If we were talking about glutamate, glutamate's alpha keto acid would be alpha keto glutarate, because it's minus 1 from the glutamate. So the alpha keto glutarate is a pair, where it's plus 1, minus 1 kind of a thing. So alpha keto acid is one step down from wherever you were starting from. Does that make sense?
So are you saying that glutamine's alpha keto acid is glutamate?
Correct.
Okay.
Glutamine's alpha keto acid is glutamate. Period. Glutamate's alpha keto acid would be alpha keto glutarate. You got it? All right. I'm going to throw up one more. that is a sequence that you will want to know. Alanine. That has one nitrogen. And if we take that away, the only difference between alanine and pyruvate is, well, that nitrogen and a few little fiddly bits, but basically you take away the alanine, and that's pyruvate. You take away the nitrogen, and that makes alanine pyruvate. Occasionally there are a few little steps in between, but we don't care about those. So, that means alanine's alpha keto acid and carbon skeleton pyruvate. All right. Any questions on this stuff? We're going to be using these terms, and that's why I kind of went into them that much.
The alpha ketoglutarate,
Mm-hmm.
what does that, so I know that it's the alpha keto acid of glutamate,
Correct. It is.
but does that have a carbon skeleton and an alpha keto itself?
So this guy has no nitrogens left, so he can't get rid of it. The carbon skeleton of alpha ketoglutarate would be itself. So once you hit the bottom, that's it. Good question. Amber.
So I thought she said something about glutamate being really important, like a key factor in, I don't know what.
Yeah.
It was just a key factor.
So glutamate, the question was, glutamate, is that a key factor? Where did that come in? So she probably was referencing glutamine, because that's going to be used to transport stuff in the blood, and we'll get there. Glutamate, if she was talking about that one, she might have been saying it's a neurotransmitter and some other things, and so you can move nitrogens around, but it itself is also important. So there are some tie-ins for both of those later in the lectures, so she could have been talking about either of them. Glutamine acts as a nitrogen transporter because it can carry a bunch. Glutamate acts as a neurotransmitter, which becomes important for stuff we see in.
Glutamine transporter, does it only go to the kidneys?
Yes, I believe that one is at least highly preferential for the kidneys. So let's go through the sequence and I'll show you that. So let's get some rows.
That's what it has, but
All right. So let's start in the muscle. Just pretend that we're breaking it down because of starvation. We've got a whole bunch of amino acids. And we are going to take those amino acids and pop the nitrogens off of them. There are 21 different kinds of amino acids, roughly, depends on where you look, 23, whatever you want to call it. And we want to take all those carbon skeletons and burn them for energy, and that means the nitrogen needs to be taken care of. The nitrogen is going to be transaminated. Trans meaning transfer, not cut loose, free to go and kill the body whenever it pleases. Transfer. If we cut it free, it's called deamination. I'll write that up. If it goes to a carrier, trans. If it's free, D. D equals free. Trans equals, well, transfer. So right here, we're going to do transamination. And we're going to transaminate it onto a bunch of pyruvate. So the 21 amino acids have given away their nitrogen. And we have an enzyme that takes it and puts it on pyruvate from those 21 guys. What will pyruvate become when it gets a nitrogen? I think I heard it.
Alanine?
Alanine. And this enzyme is named after that fact. It is called Alanine Transaminase. Alanine, A-L-T. You guys heard of or seen ALT? Liver panel. Awesome. ALT is the enzyme that's required for this, and we'll come back to it when we talk about liver panel tests. Basically, this enzyme is only found in two places, the muscle and the liver. So if you find it floating in the blood, you know that one of those two was dying and throwing all their bits into the blood. So ALT transfers the nitrogen onto the pyruvate. Pyruvate turns it into alanine and then throws it, and then the muscle throws it into the bloodstream. It floats through the blood until it arrives at our beautifully crafted liver. And then after playing Tetris, alanine, and the liver is really good at uptaking alanine. It's one reason that we transfer it in alanine. It's easier for the liver to look for one amino acid than it is 21 amino acids. So we're making it all into one. And then the liver knows alanine is usually for me. And yes, some other cells need alanine too. The liver doesn't pick it all up. It's kind of like glucose, where the liver will pick up all the extra, and it has a lower affinity than the other cells, but it will pick up the extra. Same thing here. It's going to pick up the extra alanine, and when you're dumping a bunch of alanine in the blood, lots of that will end up at the liver, and then alanine will be deaminated. And I believe that that's called alanine deaminase. If anyone can double check that enzyme name, that'd be great. But it's going to be deaminase anyway. And then that goes to the urea cycle we were talking about with the mitochondria, where this happens. So you deaminate it inside the mitochondria, and then quickly you're going to have carboxyl phosphate synthetase, pick it up, turn it into carboxyl phosphate, keep it safe. Don't let it float free. Don't let the nitrogen float free. Okay. Questions? There is more to say, but just like up to that point.
So alanine, no, deaminated alanine goes into the urea cycle? No.
So the nitrogen will be taken off of the alanine, which will make the alanine turn into pyruvate. And then the pyruvate will be burned for energy. The nitrogen is going to be the urea cycle. That nitrogen that we started with, that came from the alanine. So we've now arrived back where we started, and that'll be grabbed along with water and CO2, turned into carboxyl phosphate, go through all that stuff, and after it's been dinked around a little bit, it is urea.
And urea goes in the bloodstream?
Yes, which is our next step back into the blood. My question was going to be, and where does urea go? It does go in the blood. Wait a second. Urea in the blood. What the freak? That's actually normal. It's a heck of a lot safer than ammonia or ammonium, either of them, which are just different amounts of hydrogen on the nitrogen. And so urea, it's normal to have a low level of urea in your blood at almost any time. And the blood is all going to eventually pass by your kidneys. And your kidneys have the job of looking like a kidney bean and filtering it out. Two jobs. So all the ammonia is going to, all of the urea is going to go into the urine. So the kidneys grab it, urea goes to the kidneys and then down the ureter and all that kind of stuff. And that is a horrible attempt at a calyx, but whatever. And then the blood goes by, no more urea in the blood leaving the kidneys. So they just filter it out. Then you're okay. High urea can be toxic, so we do want to filter it out. Low urea, it's okay. All right. So now, if there aren't any questions, let's talk about what happens if the nitrogen gets free. So we talked about hyperammonemia, 1 and 2. Your mitochondria got some tanked enzymes. Yay. Let's say you have both because you're really lucky. And that means you're going to have, instead of urea going in, you're going to have this guy. Lots of this guy, lots of ammonia. And the ammonia, the kidney will try. It's not going to be very good at it. Don't worry about that. Most of the ammonia problem that we care about is that it's going to go through the blood, and it's going to be there when the blood goes by the brain. Ammonia or ammonium, either, so that NH2, NH3, both of those can cross the blood-brain barrier. No way to stop it. So they get into the brain can't say, don't come here. And if you have nitrogen, free nitrogen in the brain, it is going to bump into alpha keto glutarate. All right, fun review time. If you have enough nitrogen and it bumps into it, it doesn't need an enzyme if it hits it just the right way. If you get enough ammonia, it will hit it the right way. So this guy's going to pick up a nitrogen. Doesn't need an enzyme. Alpha ketoglutarate plus 1 nitrogen. What do we call that? Glutamate. And so in the brain, all the brain cells, this is happening on all of them, they all have alpha ketoglutarate from their TCA cycle turning into glutamate. How effective is their TCA cycle going to be? Just about nothing. Every time it starts to try to burn something, the thing that was just about to be burned for energy turns into glutamate. Glutamate is not something that goes through the TCA cycle. No energy. Brain begins to starve to death. But hey, glutamate's really good for being a neurotransmitter. I mean, at least you have a neurotransmitter. Nope. Glutamate plus a nitrogen, what do you get? Glutamine. And glutamine happens to be nice and charged, and just like glutamate, glutamine, both of them cannot cross the blood-brain barrier. So they're not going to float out into the bloodstream. They're going to stay right there. And glutamine in particular really is osmotically active, meaning where glutamine is, water follows. Kind of like where salt is, water follows. Glutamate might be, like the first reaction to glutamate, that might be starving your brain. That's not what usually kills you. It's this next one. You get water on the brain, or to be more specific, you get hydroencephalopathy. Brain starts to swell, gets too big for its cavity, and then it herniates through the foramen magnum, and basically your brain wedges itself down through your spinal cord hole. That impinges or crushes your brainstem, and that's kind of important for breathing. And so after that, we have death. And this is the one that usually causes it. Glutamine pulls in a bunch of water. Glutamine can't leave, so water has to come to it. And that's why we call ammonia toxic.
So the brainstem is forced through the foramen magnum.
Yep.
Is there any way to reverse any of that?
Once it herniates, that's it. There's nothing happening at that point. And it's also more the posterior. It's brainstem and posterior, and it just herniates however it wants to. Before it herniates, you could do like rapid dialysis if you happen to have them in the hospital or something, and it's like, oh shoot, somehow they managed to have this begin happening in the hospital. I would imagine that they'd run dialysis, but usually this is going to happen to people who have these enzymes broken, and then they didn't watch their protein intake. They ate too much protein. And then it overflows. Usually the first, if you have type 1, hard. Type 2, you can regulate it a little bit. You add a little bit of buffer, you eat a little bit of extra, and then you are like, oops. And then you have a little bit of time where it will go ahead and slowly be taken care of. Because the enzymes usually, I shouldn't say usually, sometimes the enzymes are just slower rather than completely broken. And so, but Yeah, if you started to have a reaction dialysis, and I don't know of anything else. So like taking the blood out, filtering it, putting it back in. All right, and this is pretty fast. Okay, so now let's go back over here just a little bit. We kind of got excited with like, perfect, urea goes in the blood, yes. And then I like the brain thing, it's always fun. So over here, we had 21 carbon skeletons left, right?
Mhm.
Or 20, however you want to look at it. Well, those, so the muscle, let's go ahead and notice right here, the muscle sent out like 21 pyruvate for the 21 carbon skeletons. And so it's like, that's really expensive. Pyruvate is like your energy molecule. And so it gets to burn these carbon skeletons. And all of those are worth roughly 1 pyruvate. And so it doesn't actually lose energy. It's about neutral. Because all of these guys, almost every carbon skeleton, every carbon skeleton, I think, ends up in the TCA cycle or near it. And so it'll be able to be burned. Okay, now we talked about glutamine. What about protein that comes from places besides? Go on.
Before you move down, that was a good point. So just to talk me through 21 amino acids, 21 carbons in the amino acid. What was especially 21?
Oh, 21, so you have 21 to 23 different types of amino acid. And so all of those, glutamate, glutamine, threonine, whatever you want, all of those are being changed into alanine.
Oh, they all are.
All are.
I know.
You're taking the nitrogen off of each of those types, putting it onto pyruvate, which makes it alanine. All the little bits and pieces left over, we've taken this off, we have this left, the carbon skeleton. All the carbon skeletons are going to be some kind of TCA intermediate or close enough. Occasionally there are a couple steps away and you have to tweak them, so that's why you can have 20 and it's like, there's only 8 intermediates. Yeah, well, it's close enough. Then you burn them, and the nitrogen is the rest of the story. How do we handle that? Good question. Did that clear it up?
There's 21 different potential carbon skeletons then, based on our group.
Yep.
They just don't have any amino groups.
Right. There are 21 different kinds of carbon skeletons, and probably more like 19 because there's a couple of them that degrade from like glutamine to glutamate before they hit a carbon skeleton. But the idea is, yes, there are a lot of different kinds of carbon skeletons. Was there another question?
No, I just was commenting that the body is so amazing.
Right? The body is incredible. All right. Any other questions before we hit the cell? All right, so in the cell, you are going to go ahead and make glutamine, and I believe this can also happen in the liver. Double check this one. But either way, you make glutamine and put it in the blood, wherever it came from. And then that goes through the blood and it arrives at the kidney, the person who you would expect to be doing some work in all of this process. And so glutamine, in particular, when you release that in the blood instead of alanine, then the kidney does his share of the work, so they're splitting it, and he will break glutamine into glutamate into alpha keto glutarate. And then he'll burn the alpha ketoglutarate for energy. That's not really why he did this. He did this because glutamine down to glutamate is going to give off an ammonia. But the ammonia is in the kidney, so it literally will just dump it right in the urine. Safe. Glutamate. Pull it off. Ammonia. Dump it straight into the urine. Safe. So the kidney will process the glutamine, and since it's right there, it doesn't need to have all this urea formation fancy stuff. I think it can do that too. But liver, that's like the liver's only option.
So when the kidney is using glutaminase,
Mm-hmm.
you convert it back to glutamate, then does it either become glutamine again or become alanine?
So glutaminase is an enzyme there, yes. It's going to break it down into alpha-ketoglutarate, and then it'll burn it for energy. It might also cycle the glutamate back through if it wants to and send that through the blood to be a recycled molecule. Glutamate could be recycled to go and pick up another nitrogen and come back.
Okay.
But either way, any nitrogens that are taken off, those will go into the urine, which is different than urea. Urine is after it's in the collecting tubes. And yeah. Does that make sense? Okay. If you did want to review, I feel like last week went a little bit smoother, so watch that video instead of this one. Or, you know, whatever floats your boat. So, okay, that's right, liver panel tests. Let's do that as well. All right, so we already talked about ALT, Alanine Transaminase. That's found in the muscle. It's also found, Alanine Transaminase, in the liver. And so if we find that in the blood, like we said earlier, we know it had to come from one of those two tissues beginning to die. How do we know which one? There's a second enzyme that is used in reactions that we didn't go into, but it's another transaminase, and it's aspartate transaminase, AST. Aspartate is another amino acid, so it's going to be doing some transamination and stuff, and if you're interested, you can go ahead and read into it. But this one is only found in the liver. So if you find both of these guys in the blood, you know the liver is dying. If you only find one of them in the blood, you know it's the muscle. Okie dokie.
Okay, I have a question.
Please.
I'm looking at my slides, and the glutamate dehydrogenase enzyme is positive allosteric effector of the formation. ATP and GTP are positive allosteric effectors of the formation of glutamate. Can you explain why?
Okay. So, question was, if ATP and GTP are around, why does the enzyme glutamate dehydrogenase get turned on in the direction of making more
Because it takes energy.
glutamate? Because we have energy, and therefore we don't need the alpha ketoglutarate. We could burn this for energy, or we could make it into a useful thing that we haven't just barely eaten protein in this case and we want to make more muscle. Hey, let's go ahead and make some glutamate. Or we want to make some proteins inside the cell. This is a way to make those. Glutamate dehydrogenase, by the way, is going to be the enzyme that goes in between glutamate and alpha-ketoglutarate. Wherever you see that reaction, it's reversible.
So if we're low on energy, we wouldn't steal the alpha-ketoglutarate from the TCA side. So we want energy.
Right, correct. Then we want to burn it. And sometimes, remember that the liver is trying to save everyone else. So it's who is low on energy. Everyone else is low on energy. Liver doesn't care if he's okay quite as much. He's going to send stuff out. But he is regulated by that. So usually the liver will have energy and everyone else will be starving. And then the liver's like, well, I'm good. Let's go ahead and make protein for other people or whatever else he'll make for other people. Usually if it's kind of a starvation thing, he'll make ketones and stuff instead, like a couple lectures ago. Filling in a few more enzymes because that'll probably be helpful. Glutaminase. So let's actually make this a little bit bigger. Alpha keto glutarate. Am I good to erase this? Okay. Alpha keto glutarate. I'm going to just call it alpha keto G. 2 glutamate. 2 glutamine. This way we can get some enzymes in. All right, so to build or break alpha keto and the glutamate to go either way in this reaction, that's going to be glutamate dehydrogenase, and she will want you to know that enzyme. This one, to make glutamine, it's going to be glutamine synthase. And then here's the tricky bit. To break it down is a different enzyme. And that one is glutaminase. So in the kidney, we saw glutaminase, glutamate dehydrogenase, both of those the breaking down step. In the cells or the liver, they would build it, dehydrogenase, synthase, send it out in the blood, arrives at the kidney, glutaminase, dehydrogenase. So it's just a circuit. Go this way, then go this way. This one's on both sides. So, ditto. This guy, that's right, our class had so much fun with the terminology. Okay, we've talked about transamination. We've talked about deamination. There's also amination, which is adding it from nothing. So alpha ketoglutarate, if you took a free nitrogen and put it on a free nitrogen, that would be amination. If you transferred it, then that would be from another amino acid, then that would be transamination. Does that make sense?
Yes, but I have a question.
Question.
So there's one slide that I feel like it's just sort of randomly in here. Asparagine synthetase is transamidation.
Oh, geez. Okay. I really try to never say that word, if I'm honest. Transamidation, I believe that's when they're talking about two nitrogens. And the way that I have found it most helpful to go about learning the stuff is know amination, deamination, and transamination really well. Then go ahead and look at transamidation, because if you look at those all at the same time, it tends to make, at least in my experience, people's eyes believe that transamidation is when it's talking about the second nitrogen. And to be honest, I haven't looked at that in a while.
And it looks like it's only asparagine.
I have a note that says it's anytime you're working with extra amine group, anytime you're moving or adding or removing extra amine group is called amidation.
Maybe it's a synonym for transamination. I know that there was a really fun time with all of the terminology when we were going through it.
Because aspartate has one amine group and asparagine has two amino groups.
Yeah.
Okay. So it is with the two.
But
Is
it's
that what
only
the
one
slides
slide.
are confirming? Yeah.
Thank you.
It sounded like there was an understanding of transamidation. What did you guys, you have the slides in front of you, it's been a while for me. Was it because there was two, or is that something else? We want to have the right thing.
Do you have it as transamidation or just amidation?
Well, she said transamidation and then at the end she said that's amidation.
Okay.
I thought amidation was adding an additional amino group.
So that would be this
Already.
second one.
Right. So,
I
does
just-
anybody?
I just looked it up, but it says chemical reaction in which an amide reacts with an amine to generate a new amide.
Okay.
Sorry, guys.
Amine has to be in that line form.
I believe that's the case. It's been a while since I did my chem stuff, but that's what I'm remembering. So I think it is two. Two-eyed. Happy face. moving on.
Alright.
All right. No, that's good that it does get brought up because honestly, I haven't talked about it for so long because I keep avoiding it because
Well,
these three or something, but it needs to be talked about. Okay. So I think that's Biochem for today. So hopefully that was helpful. And we'll go ahead and move to Fizz.
Thank you. Can I ask one biochem?
We have 30 seconds. All right, go.
Sorry, so on the diseases, Oregon, oh my God, let me see how to pronounce this. Thank you.
No worries. Have a good one.
Organosuccinicuria
Okay.
and citrullinemia, numbers 3 and 4 on the slide.
Okay.
It looks like they're both disorders of not having deficiency in the organosuccinate synthetase.
Right.
So if they both are a deficiency of that.
So, good question, and actually that's one that I kind of like because it makes me happy. I don't know why, but it does. So, in the urea cycle, we had that ornithine, and that picks up the carbamoyl phosphate, puts those together, makes citrulline. Citrulline goes out and becomes something called arginosuccinate eventually. There's something before that, whatever it was, I don't care. And then you have arginosuccinate. Oh, no, that's when the arginine joins the citrulline. Arginine joins the citrulline, and that makes arginosuccinate. Succinate. And so then there's one more enzyme, or a couple more, honestly. And if that enzyme's broken, you're going to have a frick ton of this build up because it can't be changed into anything else. So the question was, if you have the enzyme arginosuccinate lyase or arginase broken, why do you get a lot of arginosuccinate and citrulline? The answer is, if it has nowhere to go, it will keep on accumulating because it can't be changed into anything else, even though people keep packing more of the molecule along the rest of the pathway until it hits the dead end. So then you get a frick ton of this, and that'll back up into this, and then you get a frick ton of this. But that's not nearly as deadly because you'd have to back up like 6 reactions before you get back to the nitrogen. So that's why. All right. Catch you guys in a few.
Actually, that's German. If you add a suffix to a German word or a prefix, it changes the meaning. You can do that, add in as well.